Thank you for being here today. I'm excited to share Life of a Pixel with you. When I joined the Chrome team, this talk did not exist. And I really wanted a talk like this to exist because the system was very complicated and the design docs tended to assume that you already knew a lot of stuff. And I really wanted to just trace the complete chain of causality from web content to on-screen pixels, which is pretty hard to do just by inspecting the code. The pixels are back. Which is pretty hard to do just by inspecting the code because there's a ton of indirection and asynchronicity, and there's a lot of steps that sound like they're putting pixels on the screen, but they're actually just queuing up some kind of deferred operation. So my goal for this talk is to present the entire pipeline to you in 45 minutes, visualize and motivate the existence of each step, and give you some slides that can serve as a future reference with pointers to actual code. So the slides are pretty dense, and I'm not going to talk through every single box on each screen. But if you bookmark that URL in the lower left corner, bit.ly/lifeofapixel, then you can come back to the slides whenever you want. So this talk is about how Chrome turns web content into pixels. We have web content there on the left, pixels on the right, and in the middle is all this magic that we call rendering. So I'll first talk about what we mean by content and what we mean by pixels, and then we'll dive into the magic in the middle. One of the challenges of a talk like this is that Chrome's rendering architecture is in a state of constant flux. So just be aware that in this talk, I'm showing the state of the code that is running on trunk and shipping today in the Canary channel. And in many areas, there are efforts planned or underway that change the picture dramatically. I'll mention some of those in passing, like, by the way, in the future. But I'm not going to talk too much about the stuff that isn't launched yet, because I think that you need a solid kind of baseline understanding of how things are in the present before those future efforts will even make sense to you. So content is the generic term that we use for all of the code inside a web page or the front end of a web application. And I'm just going to do 30 seconds for those of you who have never built a web page before, which is okay, don't feel bad. Content is HTML, which is text, and markup surrounding the text, like the P in the angle brackets that creates a paragraph. Then there's CSS, or style for short, which is selectors and properties. Like here we have a selector that says P, so it's selecting paragraph elements, and a property named color, whose value is red. So this style rule is telling the engine to render all paragraph elements with red text. Then there's JavaScript, or script for short, which can modify all of the above dynamically during the browsing session. So you can change the text, put new markup in, change style values on specific elements, change style rules. Basically, everything about the state of the rendering can be modified on the fly with JavaScript. There's other kinds of content like images, video, audio, WebAssembly, WebGL, Canvas, PDF. But for this talk, we're going to focus on HTML. So a real web page is just thousands of lines of HTML, CSS, JavaScript delivered in plain text over the network. There's no inherent notion of compilation or packaging like you might find on other platforms. This means that the source code for the web app is literally the input to the rendering pipeline. Architecturally, the content namespace in the Chromium codebase is responsible for everything in the red box where the content of the page appears. And it's represented by this class called Web Contents, which is the primary public interface that the content layer exposes to the embedder. And outside of content is browser UI elements like the tab strip, the address bar, the navigation buttons, the menus, etc. You might remember from John's talk that rendering happens inside a sandboxed process. This is key to Chrome's security model. So Web Contents encapsulates creating and managing render processes, and all the actual rendering that we're going to talk about happens inside the renderer process for the tab in which the web page is loaded. You probably know Blink is our name for the rendering engine. So Blink is actually a subset of the code in the renderer process underneath the content layer. And the lines around what is in Blink code versus what's outside of Blink code are sometimes a bit confusing, partly due to the history of Blink being a fork of Apple's WebKit engine. But essentially, you can think of Blink as our implementation of the semantics of the web platform. At the other end of the pipeline, we have to get pixels onto the screen using the graphics libraries provided by the underlying operating system. On most platforms today, that's a standardized API called OpenGL. On Windows, there's an extra translation into DirectX. In the future, we may support newer APIs such as Vulkan. These libraries provide low-level graphics primitives like textures and shaders and let you do things like draw this polygon at these coordinates into a buffer of virtual pixels. But obviously, they don't understand anything about the web or HTML or CSS. Okay, so now we understand what we're starting with and where we're trying to go. The overall goal of rendering can be stated as turn web content, that's HTML, CSS, JavaScript, into the right OpenGL calls to display the pixels on the screen. But as we go through the rest of the talk, let's keep in mind a second goal, which is that we want the right intermediate data structures to enable updating the rendering efficiently after it's produced and answering queries about it from script or other parts of the system. So what I'm going to describe is a pipeline or a life cycle. And of course, it starts with content, ends with pixels, but it's broken into a bunch of stages. So it'll turn content into something and then turn that thing into something else, etc. And partly because rendering is too complicated to express as one operation, but also because those intermediate data structures let us update the rendering efficiently later on. Remember, that's goal number 2. Because maybe we don't need to run all those stages for every update. And once we finish describing the first version of our pipeline, I'm going to come back to this notion of updating the rendering and introduce some new concepts that help us optimize it. So let's jump into the first stage. We're in Blink code now in the renderer process. And the first resource that comes down from the network connection is typically HTML. And the page will have other resource types, CSS, JavaScript, images, etc. But those are brought in directly or indirectly by the HTML in the initial response. So our starting point for rendering is the HTML parser, which receives a stream of tags and text. HTML tags impose a semantically meaningful hierarchical structure on the document. For example, a div may create 2 paragraphs, each with text. So the first step in rendering is to parse those tags to build an object model that reflects this structure. We call this the document object model, or DOM for short. The DOM is a tree of the sort found in computer science, where the trees are upside down. This is the first of many trees that we'll encounter in the engine. And the reason they're all trees is that they're all based directly or indirectly on the DOM, which is based on the structure of HTML. And the nodes of the DOM tree are, not surprisingly, called DOM nodes. The DOM serves double duty as both the internal representation of the page and the API exposed to JavaScript for querying or modifying the rendering. So the V8 JavaScript engine exposes DOM web APIs as thin wrappers around the real DOM tree through a system called bindings. Now that we've built the DOM tree, it's time to look at the CSS styles. Remember, CSS has selectors and properties. So a CSS selector selects a subset of DOM nodes that its property declarations should apply to. In this case, that's the 2 paragraph elements. And style properties are the control knobs that web authors use to customize the rendering of DOM elements. So any setting you might imagine for changing formatting or colors or margins or positioning, there's probably a style property for it. Now, not only are there lots and lots of style properties, but it can be non-trivial to determine which elements a style rule actually applies to. Like this one is every other paragraph inside any div without the class foo. And some elements may be selected by more than one rule with conflicting declarations for a particular style property. So the style engine is tasked with sorting all this out. So when we first encounter a style sheet, we parse the CSS text into an object model of the style rules, which has rich representations of the selectors and the property value mappings. And these style rules are indexed in various ways for efficient lookup. Another thing to note here is that the C++ classes that implement the individual style properties, like that border left color class, are auto-generated at build time by Python scripts. The second thing we have to do is figure out how those styles apply to our DOM elements. And this is called style resolution or style recalc. In this stage, we take all the parsed style rules from the active style sheets in the document, including a set of default styles supplied by the browser, and compute the final value of every style property for every DOM element. And these are stored in an object called computed style, which is just a giant map of style properties to values. So the computed style hangs off the element and says, this element is red and italicized and has a 2-inch margin or whatever. And this is the output of the style engine. If you want to play around with this, the computed style of a DOM element is exposed to Chrome developer tools and to JavaScript. So you can highlight an element and look for that tab that says computed. And those values are coming mostly unchanged from the Blink computed style object, although a few properties actually get augmented with layout information, which we'll talk about later. So now that we've built the DOM and computed all the styles, the next step is to determine the visual geometry of all the elements. So for a block level element, we're computing the coordinates of a rectangle corresponding to the geometric region of the content area that that element occupies. In the simplest case, layout just places blocks one after another in DOM order, descending vertically. We call this block flow because the blocks flow down the page. Although note that even the simple case has a fair amount of complexity because each block's position depends on the height of its predecessor. And to know the height of a block, we have to find the line breaks, which requires measuring runs of text using the font from the computed style. So this all happens as part of layout. Layout often computes multiple kinds of bounding rects for a single layout object. For example, if the contents or DOM descendants of an element are larger than the element's declared border box, we have a situation called overflow. And layout has to keep track of both the border box rect and the layout overflow rect. The interesting thing about overflow is that you can make it scrollable. So another side effect of layout is computing scroll boundaries and reserving space for the scroll bars. The most common scrollable DOM node, of course, is the document itself, which is the root of the tree. But you can make any DOM node scrollable with CSS. And more complex layouts are needed for things like table elements or styles that specify things like breaking content into multiple columns or floating objects that sit to one side with content flowing around them, or East Asian languages that have text running vertically instead of horizontally. But notice in each case how DOM structure and computed style values like float left are inputs to the layout algorithm. So each pipeline stage is using results of the previous stages and producing outputs that influence future stages. So all of this layout information is stored in a separate tree linked to the DOM. We call this the layout tree. And the nodes in this tree implement the layout algorithms. So there's a bunch of layout classes like layout box, layout inline, layout table, etc., depending on what layout algorithm the element needs to use. But they all inherit from this common base class layout object. So every node in the layout tree is a layout object. DOM nodes are roughly one-to-one with layout objects, with a few exceptions. So for example, if you set display none on a node, then it doesn't create a layout object. And sometimes you can have a layout object with no node, and it's even possible in strange cases for a node to have more than one layout object. So we sometimes talk about DOM nodes and layout objects as if they have a direct correspondence, but just be aware that you can't always assume that's the case. So the layout stage walks the layout tree. So there's actually another stage after style recalc, which is constructing the layout tree. But when the layout tree is first constructed, none of the geometry data is filled in yet. So this update layout method walks the layout tree and fills in all the geometry data, processing side effects of the geometry, like calculating the overflow, finding line breaks, and setting up scroll containers. So one problem with the current architecture is that layout objects contain both inputs and outputs of the layout stage without a clean separation between them. For example, the layout object actually acquires ownership of its element's computed style after it's created. So a new layout system called Layout NG, that stands for Next Generation, is trying to create a cleaner separation between inputs and outputs and make it easier to build new layout algorithms. But that's under construction in the future. Now that we understand the geometry of our layout objects, it's time to paint them. So paint records paint operations into a list of display items. And a paint operation might be something like draw a rectangle at these coordinates in this color. And there are multiple display items for each layout object corresponding to like different parts of its visual appearance, like the background, the foreground, the outline, etc. And notice that we're just building a recording of paint ops that can be played back later. We're not actually executing them yet. And we'll see why that's useful in a little bit. It's important to paint elements in the right order so that they stack correctly when they overlap. So paint uses something called stacking order, which is a little different from DOM order because it can be controlled by a style property called z-index. So in this example, the yellow box comes first in DOM order, but paints after the green box, so it appears on top. It's even possible for an element to be partly in front of and partly behind another element. So that's because paint runs in multiple phases, and each paint phase does its own traversal of the subtree under a route that we call the stacking context. So now the blue box paints after the green box within each phase, but the background phase paints all the backgrounds before the foreground phase paints any of the text. So the paint ops in a display item list are executed by a process called rasterization. And rasterization turns a display item list or some portion of a display item list into a bitmap of color values. And each cell in the bitmap holds values for 4 color channels. The rastered bitmap is stored in memory, typically GPU memory, referenced by an OpenGL texture object. The GPU can not only store the output, but it can also run the commands that produce the bitmap, and that's a mode we call accelerated rasterization, or GPU rasterization. Keep in mind, so far these pixels are just in memory, so they're not on the screen yet. To build the bitmap, rasterization issues OpenGL calls through a library called Skia. And Skia provides a layer of abstraction around the hardware and understands more complex things like paths and Bezier curves. So when it's time to raster our display item, those paint ops make calls to this SK canvas object inside Skia. And that goes through some more layers. In fact, Skia's GPU accelerated code path builds its own buffer of drawing operations, which is flushed at the end of the raster task. But during that flush, we get to the actual GL commands that build the texture. Skia is open source and maintained by Google. It ships in the Chrome binary, but it lives in a separate code repository. And it's also used by some other products, such as the Android operating system. Okay, so the last slide was a bit of a lie because I made it look like Skia called directly into the system OpenGL. But remember, the renderer process is sandboxed, so it can't make system calls directly. So those GL calls issued by Skia in the renderer are actually proxied into a different process called the GPU process using something called a command buffer. So the GPU process receives the command buffer and it issues the real GL calls through a set of function pointers on this GL API object. The GPU process exists for a couple of reasons. One is that we need to escape the renderer sandbox, like I mentioned. The other is that graphics drivers that OpenGL uses are often unstable or have security vulnerabilities. And isolating GL in the GPU process gives us some protection from that. Like if the GPU process crashes, the browser can start it back up again. On most platforms, those GL API function pointers are initialized by dynamic lookup from the system's shared OpenGL library. On Windows, they come from a library that we provide called Angle, represented by the red box that's at an angle. Angle's job is to translate OpenGL to DirectX, which is Microsoft's API for accelerated graphics on Windows. There are also OpenGL drivers on Windows, but I'm told that historically they've not been very high quality, so we didn't want to use them. In the future, raster is going to happen in the GPU process instead of the renderer process. That means the IPC channel is carrying paint ops instead of GPU command buffers. This is supposed to improve performance, and I'm told that it's also needed to support Vulkan, which is the next generation replacement for OpenGL. Okay, let's review. We've now gone all the way from content through DOM, style, layout, paint, raster, and GPU to pixels in memory. But it's about to get more complicated. To motivate this, first remember that the rendering is not static. There are all kinds of things happening during the browsing session that can change the rendering dynamically. And running the full pipeline is expensive. So we want to avoid unnecessary work as much as possible. So to think about change over time, we have this concept of animation frames. Each frame is a complete rendering of the state of the content at a particular point in time. And when we want smooth motion, like for scrolling or zooming or CSS animations of page elements, the gold standard is like 60 frames per second, which is the VSync interval on typical display hardware. That means if we take more than 1/60th of a second to render the frame, the motion will stutter and look janky. So one obvious optimization is to keep track of what's changed and reuse things that haven't changed. So each pipeline stage has its own concept of granular invalidation, where you can say, for example, this node needs its layout recomputed on the next frame. And then the next layout pass will lay out only the nodes that have been marked as needing layout. So that helps, but it only gets you so far, especially if you're transforming a large visual region, which is common for animations and scrolling. Rerunning paint and raster for the entire region after every scroll event is quite expensive. And the other thing to keep in mind is that everything on the main thread competes with JavaScript. So even if your rendering pipeline was super fast, you'd still get jank if script is doing something expensive before the rendering even starts. And the DOM lives on the main thread, so anything in the pipeline that interacts with the DOM also has to live on the main thread. So this sets the stage for the next big optimization, which we call compositing. And the compositor introduces two fundamental ideas. One is break the page into layers, and the other is combine them on a separate thread. So a layer is like a piece of the web page that can be transformed and rastered independently of the other layers. If you've ever played with layers in Photoshop, it's a similar concept. DevTools even gives you a cool 3D view of the layers, which you can see on the right there. The compositor thread is called the impl thread, which doesn't make much sense, but it's all over the code, but it's useful to make that association in your head. So all the important cases of fluid motion of part of the page can be expressed in terms of composited layers. Like we can have layers transformed by animation or scrolling or pinch zoom, and scroll containers can clip a layer of scrolling content so that it's only visible within a certain region. And that means the compositor thread has everything it needs to handle scroll input events, while the main thread is busy with other things like JavaScript. So the browser process gets input from the operating system that the user has moved their finger on the touch screen, and it forwards that into the renderer, where the compositor thread gets the first crack at handling it. And if it's just scrolling a composited layer, then the compositor can do that without even talking to the main thread. But in more complicated situations, the compositor might say, no, I can't handle that. Let's forward it to the main thread. And it goes into the main thread's message queue for whenever it gets around to it. Okay, so how are layers stored? Layers are, big surprise, also a tree. And the structure of the tree determines how the layers stack and apply effects. Some layers don't actually draw content of their own, but they exist to apply clipping or other effects like opacity or reflection to their descendant layers. Layers in compositing generally live in the CC namespace, which stands for Chromium Compositor, so that's why you see CC layer all over the place. And the layer tree is based on the layout tree indirectly. So, for example, certain style properties will cause a layer to be created for a layout object. And if a layout object doesn't have a layer, it paints into the layer of the nearest ancestor that has one. So you can think of these layers as capturing subtrees of the DOM. The other thing to note here is an intermediate step called the paint layer tree before the CC layer tree. And paint layers are like candidates for layerization. So having a paint layer is necessary but not sufficient for an element to get its own CC layer. Elements that are scroll containers actually create a whole set of layers for things like the borders, the clip, and the scroll bars. So like each scroll bar is its own layer, and that scroll corner in between the two scroll bars is also a layer. And all those layers are managed by this composited layer mapping object, which is owned by the paint layer. So now we understand what the layer tree is. How does it fit into the rendering pipeline? Building the layer tree is a new lifecycle stage called the compositing update. And today it happens after layout and before paint on the main thread. And each layer is painted separately. So if you remember the display item list, which is the output of paint, each layer has its own display item list. And the compositing update and the paint stage operate on these objects called graphics layers, which is just a blank wrapper around a CC layer object. So you can mostly think of graphics layer and CC layer interchangeably. In the future, we're going to create layers after paint instead of before paint. This is a project called Slimming Paint. And the goal of Slimming Paint is to let us make more fine-grained compositing decisions and make compositing more independent of paint order and other things. So in the Slimming Paint world, we will create layers by taking chunks of display items that share common properties. And those properties, which used to be associated with layers, are now stored in their own structures called property trees. After paint is finished, we run something called the commit, which updates a copy of the layer tree on the compositor thread to match the state of the layer tree on the main thread. The commit runs on the compositor thread with the main thread blocked so that it's safe to read the main thread's layer tree. So that's how the synchronization happens. Okay, so how does raster work in a compositing world? Remember, raster was the step that came after paint, which turns the paint ops into bitmaps. Now, layers can be large. Remember, for a scroll container, we have a layer for the entire scrolling content. So rastering the whole thing is expensive and unnecessary if only part of it is visible. So the compositor thread divides the layer into tiles. And tiles are the unit of raster work. Tiles are rastered with a pool of dedicated raster threads. So the compositor thread has an object called the tile manager, which creates the tiles and schedules raster tasks on that worker pool, prioritized based on their distance from the viewport, and each raster task produces a bitmap for a particular tile. By the way, a layer actually has multiple tilings for different resolutions, which this slide doesn't show because there's enough going on already, but just keep that in mind. So once all the tiles are rastered, the compositor thread generates these things called draw quads, and a quad is like an instruction to draw a tile in a particular location on the screen, taking into account all the transformations applied by the layer tree. So each quad references the tile's rastered output in memory, and the quads are wrapped up in a compositor frame object, which gets submitted to the browser process. Remember, we said the renderer produces animation frames. These are the frames that it's producing. So we've seen that raster and drawing both happen on the compositor thread's layer tree after the commit. But we've also seen that raster happens asynchronously on a pool of worker threads. So this creates a complication when a new commit comes in, because we'd like to continue drawing tiles from the previous commit while we're waiting for the new commit to be rastered. We solve this by having two copies of the tree on the impl thread. And the pending tree receives the commit, and when it's ready to draw, we have a step called activation, which copies the pending tree into the active tree. So now we understand how complete animation frames are produced by the renderer and submitted to the browser process. And the browser process runs a component called the display compositor. That's different from the renderer's compositor that we already talked about. And this component lives inside a service called viz, which is short for visuals. And it aggregates compositor frames submitted from all the renderers, along with frames from the browser UI outside of the web contents. Then it issues the OpenGL calls to draw the quad resources, which go to the GPU process, just like the GL calls from the raster workers. And on most platforms, the display compositor's output is double buffered, so those quads draw into a back buffer, and then we have a swap command that makes it visible. On some platforms, like on Mac, that buffering happens inside the operating system using core animation. But the end result of display compositing is that our pixels are finally on the screen where the user can see them. So a quick recap. We've taken web content, built a DOM tree, resolved styles, updated layout, created compositing layers, painted the layers into display item lists, committed the layer tree to the compositor thread, broken the layers into tiles, rastered the tiles on worker threads, copied the pending tree to the active tree, drawn the tree into quads, and submitted the quads to the browser process, and displayed them as pixels on the screen. Raster and display run GL through the GPU process, and input events for scrolling and zooming can update layers on the compositor thread while the main thread is busy. And you'll notice a yellow box labeled blink around all of the main thread lifecycle stages. That's the portion of rendering that happens strictly in Blink code. But the Blink project, broadly construed, very often ends up touching things on the compositor side to achieve the goals of the web platform. So the boundaries of code ownership are not very strict. We've reached the end of life of a pixel, which I guess is death of the pixel. If you didn't follow all the details, that's okay. I hope I've at least conveyed an impression of the big picture. If you're thinking this stuff seems more complicated than necessary, you are probably right. A lot of the complexity comes from organic evolution and design decisions that made sense at the time, but maybe don't make sense in today's world. And I hope that some of you will work on making it simpler, because we need continuous engineering investment in fighting that complexity and paying down our technical debt. Anyway, there's the link to the slides again. And if you have feedback about the talk, especially if there's anything I got wrong, please email me. I'm always thinking about ways to improve it. And with that, I'll go to questions. So let me switch to the door here. And if you want to ask live, I think there's also a mic somewhere. When we lock the layout tree, does layout information flow up the tree, objects tell their parents how big to be, or down, or some more complex combination? The answer is number 3. It is a combination of up and down. So in particular, for a simple case of block layout, your height is coming from your children, but your width is coming from your container. Because if you imagine resizing the window, the narrower window has less space to lay out the text, so it's going to break in different places. And so there's this kind of dual dependency where only part of the layout information is complete until you've traversed the descendants and added them to your height. Okay. Let's take a live question.
So originally when you started describing very early on about rasterization, you said we may use the GPU.
Mm-hmm.
In the final slide, you showed rasterization within the compositor thread, and then the final result ends up being sent to the GPU as like command buffers, which is what.
Yeah, the raster uses the GPU, and then the display compositing also uses the GPU.
So there's a separate step before that. So the thread goes to the GPU multiple times, do separate things before the final.
Remember, raster isn't putting anything on the screen. Raster is just building a texture in memory. So we're still going to the GPU to build that texture, but there's a step needed afterwards to display it. Does that make sense?
I'm just saying, like, do we go twice, like before displaying and after displaying? Because the final slide just showed the display part.
Yeah, we don't do anything after displaying. Displaying is the end. Let's do another live question.
Related questions there. So both times we go to the GPU process, do we go through the browser process? Because I think in the slide there was one proxy and the other one was a direct arrow.
Yeah, the question was, do we go through the browser process when the renderer talks to the GPU? And no, the renderer talks directly to the GPU process. So both the renderer and the browser have IPC channels to the GPU process in the current architecture. There's also the future architecture where raster moves into the GPU, but that's different. Let me do another Dory. I assume more layers Is more memory traded for better performance? How is this trade-off made? Do we have multiple modes based on available system resources? Yeah, so deciding what things should get layers is complicated, and there is definitely a memory trade-off. For example, if you have a scroller that's composited, you're allocating way more memory because you have to create a layer that's the size of the entire scrolling content. Whereas if it's not composited, then the only space that's used is the size of the scroller's viewport, so to speak. So there's definitely memory trade-offs there. I think there's also memory trade-offs happening in the tile manager, which make it not as expensive as you might think to create a layer because we're not necessarily rastering all of that layer every time. Yeah, another live question? How does Houdini fit into all this? So Houdini is an API for custom layout. And I believe the Layout NG project, which I mentioned briefly, is sort of this re-architecture of the layout engine. Houdini is one of the motivating factors there because we want to support custom layout engines, in particular those that are supplied by JavaScript. So Layout NG is sort of a step along that path. Do we have a layer limit defined? I'm not sure. I haven't seen one. I'm not positive that it doesn't exist. Just a note, if you do create a scrollable element and you want the compositor to handle scrolling without the main thread, then you need to tell the renderer to create a new layer with will change transform. Otherwise, compositor scrolling breaks. Yes, this is correct. Although it depends on whether you're high DPI or low DPI. So if you're high DPI, like a Retina display on a Mac, then we composite all the scrollers by default, so you don't need will change transform. And we'll also composite them if they have opaque backgrounds. So there's a bunch of different conditions that we look at. But yeah, will change transform is the way to force layerization in web content. How does UPIF change this process? I'm slightly out of my depth here, but I believe UPIF is relevant to the display compositor because the display compositor is getting compositor frames from different renderer processes and using them to build what we display in the tab. So if you have out-of-process iframes, then your tab is not just one renderer, but multiple renderers, and they're all submitting separate compositor frames. So UPIF complicates the requirements of Viz. Someone who works on Viz could probably give you a much better answer than that, but that's about what I know. Any other live questions? We can do a few more. How are we on time? How do we manage the notion of time, for example, for animations? So animations are driven by the VSync signal. So on most displays, it's like 60 frames a second. We're queuing up like a task to generate a new animation frame. Of course, that's dependent on our ability to actually produce that frame within that time budget. So if the rendering is too complex and it takes more than 1/60th of a second, then your animation gets slower. Thank you very much for listening, and enjoy the rest of your day.